Okay, so now we're going to actually show you how to um, program the solutions to the LRC circuit um, numerically, and I'm going to do it in Excel first so that way you can see what exactly is going on. And then we will do it in Python. So I already have the Python code pre-written, and we will then go through and comment on the code. Um, and so you can see what's going on. So first things first, recap, right? So we have the algorithm to calculate the final current in terms of the resistance, the initial current, the initial charge, the capacitance, the inductance, our time interval, and our initial current. And the final charge in terms of the final current that we just calculated multiplied by our time interval and the initial current, or initial charge rather. So this is what we're going to do. And so here is an example. And so I've already got this program, but again, I'll walk through this with you step by step so you can see what's happening. And you can see that I already have a plot, and this is a lowercase l. This should actually be an uppercase L. So this is the current, I'm sorry, not L, but I. This should be the current versus time. And this is the charge versus time. But okay, so here's the thought process behind all of this. So here's my column of time intervals, and here's the current that's calculated with the algorithm we just showed, and here is the charge. Now, first things first, I've come over here and I've specified values for the inductance, for the resistance, and for the charge, and for the voltage that the capacitor is initially charged to. Okay, so with that in mind, I can calculate the initial charge on the plates by multiplying the voltage by the capacitance. Remember, Q is equal to CV. So this is just taking the capacitance multiplied by the voltage to get the initial charge. And this is the value that I've set the initial amount of charge to. So as you can see, the cell here is equal to B6. I don't know if I can increase the size of the font of the formula bar, so I apologize if that's not terribly clear. But the dollar signs, for those who might not be terribly familiar with Excel, the dollar signs basically hold that value constant. Okay. Now, I actually don't need those dollar signs here because this is the only cell that I don't have an explicit formula, this formula, okay, because we have to set our initial values. So these first two cells for my current and my charge are my initial values. My current doesn't flow immediately, so my initial current is 0. And the initial charge on the plates is the voltage it was charged to multiplied by the capacitance. The time interval is extremely important. Okay, now we're not going to go into all of the nuances of how to optimize what time interval you want to use, but you do want to use a time interval that is relatively short, and you want to use one that is shorter than the resonant frequency of the system, Because if you don't use a time interval that is smaller than that, then instabilities in your algorithm are going to grow very, very, very quickly. So we can actually calculate what the resonant frequency is. Maybe label it omega resonance, right? And remember that this is going to be 1 over the square root of the inductance multiplied by the capacitance. Okay, so my resonant frequency is 7.07 e to the 1. So this means that I'm going to be oscillating. This is the angular frequency. I really should specify that. So the regular frequency is going to equal 1 over 2 pi times that, right? Now, this is 70, right? So 7.07 times 10 to the first is 70.7. And so when I divide that by 2 pi, I get 11.3. So what this is saying is in 1 second I should have about 11 cycles of the oscillations, and let's see if that's true. So if my system starts at 0 going down, I would get 1 cycle here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, very close to 11. So that tells us that we've nailed the correct resonant frequency. All right. So now what does this have to do with our time intervals? Okay, so the period, the resonant period, is going to be 1 over that in seconds. So my resonant period is going to be about 8.89 times 10 to the negative 2, or very close to 0.01. And the closer or larger to that value I use, then the faster these instabilities are going to grow. So watch what happens to my chart. And so for right now, before we actually get into the algorithm, you'll notice that my chart is a nice decaying sinusoid with the exponential decay bounding it on both sides. And this holds for both the current and the charge, as it should. Right? So we have this form. And so watch what happens if I choose a much smaller value for my time interval. If I go to 0.01. Okay. Now, if I do that, then I haven't oversampled yet, right? But watch what happens if I change the capacitance. Let's change the capacitance from its current value of 1 times 10 to the negative 4, or 100 microcoulombs. Let's change that to 10 microcoulombs. And now you can see that my axes have blown up, right? So what's going on now is that my period is, or my time interval is not smaller than my resonant period. And so this means that I'm not sampling the system correctly, right? And so if I put another 0 back in, I actually recover the oscillatory nature of my system. And so your step size is incredibly important in your choice, right? So for the moment, we'll just say our step size is incredibly important. And originally, I had this at 1, so we can see what happens there. And so the smaller I make my inductor, the more this will die out. Okay, the faster this will die out. And we should understand the physics for that at this point. The smaller my inductor, the less EMF, the less back EMF it's going to push. And so effectively this is going to allow the capacitor to simply discharge faster through the resistor. The resistor is going to dissipate the power of the current through the circuit. I really should put it that way. But in any case. Okay, and by the way, one more thing that you might want to calculate, if you really want to, if you come back to this expression, okay, this expression will tell you what the critical frequency is, because when this expression is 0, or when r squared is equal to 4L over C, that is your resistance at which you achieve critical damping. So we can even get an algorithm to tell us, oh, wait a minute, what is my critical resistance? And how close is my specified resistance to that? So what if we put our critical? So we would have to set R is going to equal the square root of 4L over C. Okay, so this is going to equal the square root of 4 times L over C, and it's 200. So we can even see what happens if I put 200 in for my resistance here. And if I do that, okay, so now I have that nature where I don't have any oscillation. My system will go down, and then when it comes back up, effectively that will cause the current to die out very quickly. And if I go over that amount, let's say 500, then I achieve an even steeper drop on my current, or a sharper drop on my charge, and my system just dies out. So you can play with what happens here. And when I get near the critical damping but not quite there, you can see that I have one oscillation here, it looks like. And as I move away from that again, then I'm going to get a little bit more oscillations as I decrease my resistance. And let's go down to 40. And then you really start to see the solution that we found here. Right. So again, this is when R was below that critical value, is when this solution holds. Okay. So and this is what we really want to see. This is the part that I want to show you. So this is good. This is what we've got. Okay. So now how do we actually program it? That was a really long-winded way of saying how do we actually do it. So once you have your initial values specified, your inductance, your resistance, capacitance, voltage, calculate your initial charge, choose your step size. So what I did here in the time column, I just specified 0 as my start time, and then I took that value and added my time step, right? And then added my time step again. So I basically click and dragged in here and did this for a total of 1,000 steps. So if my time step is 0.001, 1,000th, for 1,000 times, then I get 1 full second. And that's what we have down here. All right. Okay, so my current I initially specified to 0, my charge to the value calculated from Q times, C times V. Now, the next value of my current, this is where this formula actually comes into play. Okay, this is where this formula actually comes into play. And this formula is this formula here. Okay, so I'm taking the negative quantity of R times I initial plus Q initial over C divided by the inductance multiplied by the time plus I initial. So let's confirm that's what we have. R times I initial. So B2, I'm going to undo that. So B2 is my R. Time, and again, since these values are specified, these are wrapped in dollar signs to keep their values constant. Times G2. G2 is the initial current that I have right here, plus H2, which is the initial charge. So initial charge divided by the capacitance. H2 divided by B3. B3 is the capacitance. All with a negative sign. Divided by B1, which is the inductance. Multiplied by B8, which is the time interval. Plus G2, which is the initial time. So once you have that programmed in, you can just hit enter. Okay. And if you haven't clicked and dragged all the way down, you won't see anything in these cells here. And then you can come over here to the charge column and input this formula. Your final charge is equal to your final current that you just calculated. So this is going to be equal to G3, which is the current that I just calculated, times B8, which is my time interval, plus H2, the previous charge. So that's it. Once you have these formulas, you can then calculate the updated current and charge through the circuit and on the plate respectively at each time step, each increment of 0.001 seconds. Or if you really wanted to, you could do this for a 10,000th of a second, and you would get a smaller portion of your cycle. If you didn't want to do that, you could do 5 10,000ths, and that would give you a bit more of the overall behavior. But whatever this is, I don't want to fiddle with this too much. But there it is, right? So there's your system, and you've got your exponential decay bounding your decaying oscillations, okay? And so once you have these in here, right, once you actually get these formulas in here, all you have to do is highlight both of these rows and drag down. And you can click and drag those formulas and they will automatically populate. And now, of course, mine were already done, but you can do that and they will automatically fill in. So once you have your formulas, you're good to go. Okay, let's translate this into Python, right? So here we've got the code, and what I'm going to do is I'm going to open up Python Baba. Come down here. And I'm going to copy and paste so that way I have a little bit more control over the font size because it's a little small here. So first things first, we'll copy and paste, and we will make sure that it works. Okay, so sure enough, right? And first things first, the code, one times 10 to the negative 4. 1 times 10 to the negative 4. Oh, yes. Okay. So I wanted to make sure the values were agreeing. So here what we've got, right? First, let me explain a little bit about the output and then what the program is doing. So I did a no, okay, and did not label my axes. I really should. We'll actually label the axes as we go through and comment on the code. But the top graph is your current, so that is the this graph. And the second graph is a mixture of a few things. Number one, the black is the actual decaying solution for the charge. So the black line represents this function right here. Okay. The black represents this function right here, the exponential decay combined with the oscillation. The green is actually the bounding exponential decay, and that is just to ensure that we calculated the exponential, or really that we calculated the solution correctly, because if we didn't, then the exponential decay might not run right exactly across the top of that bounding line. And the red is the solution to the system if I were to set the resistance down to 0, and I would just have pure oscillations in the LC circuit like we've observed before. If R is 0, okay, if R is 0, then remember e to the 0 is 1, and so this would just be Q0 times the cosine of the resonant frequency. And so it would just be a pure oscillation. So that's, and this is to make sure that the decaying oscillations stay lined up with the natural oscillation that the system would have. So that's the output. So how did we get here? Okay, so let's comment through this code and see if we can understand it a little bit better. Number one, we're just importing our libraries. Okay. So number two, this is going to specify the parameters of the circuit. Okay. So this is the inductance. Oop. This is the capacitance. This is the voltage. Omega, this is the natural resonant frequency. Right. So for the moment, actually, let's expand this out just a little bit. So this just prints what the natural resonant frequency is. And I'm actually going to put angular in here. Okay. And then this just prints a line, so that way I'm not putting all my text right on top of each other and there's a natural break. It's easier on the eyes. So the equilibrium resistance, okay, And so L over 2 times omega. Remember that omega is 1 over square root LC. Okay, 1 over square root LC. And so if I were to write this in terms of the angular frequency, 1 over LC, then I would multiply both the top and the bottom by L, and I would get 4L squared over LC. And remember, the natural resonant frequency is when this quantity equals R squared. So when I take the square root, I would get the square root of 4L squared over LC. And so 4L squared would come out of the square root as 2L, and I would be left with 1 over square root LC. So that is 2L over square root LC. So that's where this calculation comes from. And then this just prints the equilibrium resistance. Okay, I really should say critical resistance. And maybe, and this is just for you to know what that value is, so that way you can then specify your resistance however you would like. Okay, so now we're going to specify the specify the time and number of points. Okay, so this is going to specify our time range and the number of points we want to take into account. So this T equals NP dot A range. This tells me to make an array, or this tells Python rather to make an array from 0 to 0.5 in increments of 0.001. Okay, so this specifies our time array and interval. And if I come back over here, whoop, okay, so this specifies our time interval. The time between the second and first data point is going to be the time interval that we're going to use. And this specifies so the reason, okay, I really should put it this way. Specifies the number of points in the time interval. Yeah. Right, so I really should put it like that. I really should word it like that. And we'll see why here in just a minute. So this is going to be my resistance. And this is going to be the array for my current and charge. And this specifies the initial value for your charge. And this specifies the initial value for current. Okay, now let me come back to Excel for just a moment, and I'll talk about this, the code for T, DT, and N right here. Now, I arbitrarily set what dt was, and then I built my t array off of that, right? What Python is doing with this A-range code is saying, okay, I know the numbers that I want to go between 0 and 0.5 seconds, and I want to do so in this interval. And so then what is the difference between the first and the 0th element? And if my interval is 0.001 as I've specified, then the difference between those should be 0.001. So you can print dt just to make sure that it is what you expected it to be. But here we're basically letting the array specify what dt is for us. And here we're specifying what dt is and then letting the array build itself. But so in Excel here, I went for 1 whole second instead of 0.5, but the point will still stand. Let's just assume I went for 0.5 seconds. So I'm looking at these total number of times. Whoop. Come back up. So, okay, so 0.5. How many points in this array do I have? Well, if I count backwards from 0.5 down to 0.001, that would be 500 points. The initial time gives me 501 points. So there are actually 501, or n would equal 501 in this case. Okay. N would equal 501. But I don't have to calculate with any algorithms what the first data point is, the initial data point, I should say. We don't have to calculate what this is because this is specified by the system. This is the initial charge multiplied by the capacitance. This is going to be 0 because the current hasn't grown yet. So I don't have to calculate via the algorithm what these values are, so I actually only need to do the algorithm 500 times for this 0.001 up through 0.5 values. Okay, so that will be important. Right here, as a matter of fact. So this is the meat of the program. Okay, so this is the Euler-Cromer differential equation algorithm, and this is basically what we had specified in this cell for I. We're going to take the resistance, multiply it by the initial current, plus the charge, initial charge, divided by the capacitance, divided by the inductance, multiplied by the time, and then plus the previous current. So that is what this term is right here. This is the algorithm for that. But before we get there, note that the n-1 is because initial values were already specified right here. So my initial array for my charge, now these were all set to zeros, right? But there's 501 zeros in here, okay? And then the first element is then specified with these initial conditions, and then I only need to do the loop one less time, okay, or n-1 times. So n-1 because the 0th element of I and Q already specified. Okay, so that's why we have the n-1. I have 501 elements. One of those is already specified, so I need to do it 500 more times. And so this is the algorithm that updates the next element of charge. So basically what this is doing, for I in range n minus 1, unless you specify I to be something else, it's going to take I equal to 0 initially. So I equal to 0 would be the 0th elements, right? But I've already specified those, so I need to calculate the I plus 1 elements. Okay, I need to calculate the I plus 1 elements. So what this is going to do, this is going to go from n minus 1, or from 0 to n minus 1. And so if it goes from 0 to n minus 1 for 500 times, I is going to go from 0 to 499. So I'm then going to calculate elements 1 through 500, because I starts at 0, plus 1 is 1. So the first calculation this does is going to update the I equals 1 element in both arrays. And it's going to do that 500 times. And so the last I value is going to be 499, and 499 plus 1, I plus 1, I plus 1, is going to be the 5th 100 element. So this loop is going to terminate after it calculates the last value. Okay. Now this is the forward method, because you could put a piece of code right here that says I starts at 1, because you want to specify if I make a list of my I's, so this would be the 0th index, this is the first index, 2nd, 3rd, 4th, 5th, 6th, 7th, and so on, dot, dot, dot. Okay. Because I'm starting here, I could go ahead and say I want I to start at 1. And in that case, what you would do is you would leave the plus 1, or you would take the plus 1 out here, and you would say, but I want this to be the previous current value, so this would be I minus 1, and this would be charge minus 1. Okay, so that would be kind of a backward difference formula as opposed to a forward distance or a forward difference formula. So you can do it either way, but to me this is slightly more intuitive, and you don't have to worry about this extra piece of code right here. You don't have to worry about what you're setting your I value equal to. Right. So this piece of code calculates the current, array values, and this calculates the charge. Now I should also mention one more thing, okay? The Euler-Cromer differential equation algorithm comes in because when you're doing your second calculation here, you're actually using the result of the previous calculation, not the initial previous value of the charge or the current. So when we do our updating for the charge here, I'm going to use the value for the current that I just found instead of the previous value. That's the Euler-Cromer correction to the simple so-called Euler method. Okay. And especially when you get into second order differential equations, the Euler-Cromer is usually by far better than the Euler method. Now, there are more sophisticated algorithms than this, right? I cannot specify that enough. And I'll actually show you guys how to do some like Runge-Kutta algorithms at some point. But if you just need a quick solution that's still very accurate In most cases, especially with judiciously chosen input values and time intervals, this is a relatively quick and easy way because every differential equation can be written as a difference equation. Every differential equation can be written as a difference equation like this and put into terms where you're updating your new elements in terms of your previous ones. And so this is a very efficient code to write, and it can be very clean and easy to debug. So if you don't need terribly high precision and you don't want to spend a lot of time debugging things that will potentially have a lot of problems with them, if you type a plus sign where a minus sign ought to be, it can take a really long time with other more sophisticated algorithms with several lines of computation to find those mistakes. Whereas with the Euler-Cromer method, this is a relatively easy code to parse, relatively easy code to digest, relatively easy code to look at, and therefore it is preferable in many ways, especially when starting out. So I can't say that enough. Okay, so this is the heart of the code. This is what's actually doing the calculations, and this is updating with each step the values of our I and our Q arrays. Okay, so these are the arrays that we're actually plotting against our time array in these plots over here. Now this Q is this Q omega. Okay, this Q this Q naught times NP cos omega t is this formula without the exponential function. In other words, when the exponential function goes to 1 or the resistance goes to 0 and I just have pure sinusoids, this is the formula that I would get. And Q naught here, too far. Q naught, the voltage times the capacitance, is the amplitude of the normal oscillations in the LC circuit. So the red oscillations over here. So this will eventually be the function that's plotted in the red. Okay, so this is the oscillatory solution when R equals 0, right? And this is just the exponential decay term along with the leading coefficient, Q naught e to the negative R over 2L times t, because we know that the oscillations should be dampened by this value, and what that means is the exponential decay should be bounded. So we should find the as the oscillations decay and the functions that bound those two opposite sides of the time axis should be exponential functions. Now I didn't plot this one, just plotted this one, but under the assumption that if this one turned out correct, then we can assume that this one is correct as well. So if you want to, you can also plot that one, but that's what this function is. So this is the exponential decay function. So this, we'll label this the exponential decay part of the general solution. Okay, so now this actually plots some things. So this will plot, this top one plots my current against my time. So I'm going to plot my time on the x-axis, my current on the y-axis, and this is going to be a blue line. Okay, so we've got that. And if we want, we can add our axes labels. And so this is going to plot the general charge solution in black, the R equals 0 oscillatory solution in red, and the exponential decay in green. So when we plot this, right, I've already specified Q, lowercase q, is my oscillatory solution. So that's what I'm plotting here, right? So time versus my regular oscillatory solution, lowercase q. Capital Q was defined as the variable in the array that I updated with the Euler-Cromer calculation. So capital Q is the array that stores the general solution, and qexp is the exponential decay function. And so that's what all of these are doing. And if we want to, we can do the same thing. So PLT, and actually, well, I was going to copy and paste, but I'll just go ahead and type it out, so it won't take that much longer. Okay, so now we should be good to go. And if we run this, that's because I changed R critical. So this should be R crit. And there we go. And there we go. So, and as you can see, the values do decay as predicted and as agreed on in Excel. Now in Excel, once again, I went out to 1 second, and here I only went to 0.5 seconds, but the agreement is still there, right? The oscillatory solution is found numerically, right? So, or would be found numerically, and we can actually show that if we set R equal to 0. Watch what happens. And there is no exponential decay. The green line is flat. And the green line is flat because the exponential decay has the coefficient of Q naught. So whatever the initial charge is, that green line's just going to stay there. But notice, okay, the black and the red are lying right on top of each other. So this is a very stable algorithm. And actually, as a matter of fact, if I change this to just an Euler method, so as I mentioned, it's this portion right here that defines the Euler-Cromer method. If the regular Euler method just uses all previous values in all cases when updating your new values. And so if I run this code, you can see instabilities grow rather rapidly. And this is a consequence of the Euler method is a very good method when you have a one-dimensional differential equation. When you have a two-dimensional differential equation, using the previous values in your original derivative function, and well, in this case, when I say derivative function, what I mean is using this function, right? So I is equal to the derivative of charge over time, and I use this function to calculate the final charge. The regular Euler method would say this would be equal to the initial current, but because this is a second order differential equation, instabilities when you do that grow very rapidly, and so incorporating the most recent value for your current into this calculation stabilizes it. So that is why when I do this, then my solutions make sense again, right? And as a matter of fact, it'll be interesting and instructive to run the code like this and see what this does. So you'll notice it actually doesn't look all that weird. And so this is because before we had set the resistance equal to 0. Now we're setting it back to 20. And so it's actually causing the system to decay out like normal. And if you just looked at this plot, and if you just looked at the black plot, you may be led into a false sense of security that your code was working well. But as you can see, the exact solution for the exponential decay does not exactly bound the peaks of the black function. And so that's a sign that something is not right. And I could increase the accuracy of the Euler method by choosing smaller and smaller time intervals. But when you do that, it's okay for this kind of thing. But when you have a really complex computation and you want to be as efficient as possible, I've just done 10 times as many computations, actually really 20 times because I did them both twice, as before. So if you can get away with doing 10 times fewer computation as before, then you can write much more complex code as you move forward. So this is why I prefer the Euler-Cromer method. It's more stable over different time intervals, and it doesn't have the growing instabilities in the same way that the Euler method does. Now, not to say that there aren't numerical issues with the Euler-Cromer method, but for a simple system like this, those issues, especially when you're just simply getting a visual sense of what's going on and you don't have to worry about your round-off error, it can be quite useful. So this is how to, or one method to with which to solve differential equations using numerical techniques. And this technique can be applied to any differential equation if you have sufficient input with all the necessary parameters. And so it's a very, very powerful tool. So I hope that you may have found this video helpful, and we will talk with you in the next lesson.